I'm the research associate of the Nuance EPIC Center. I'm totally working on the in situ works of the TEMs, including the liquid gas heating. Today, I want to introduce the introduction and application of the atmosphere system in our EPIC Center. If you have some question, please post it on the chat. I will look at the questions and answer them at the end of the presentation. So I will talk about in the following topics, these 5 parts to cover the presentation. The first one, what is in situ? We're always talking about in situ. So when we talk about in situ, the word original comes from the Latin first. That means that it's locally on site and is where an event takes place and is used in many different contexts. If we, when we apply the in situ in TM, we mean the in situ scanning and transmission electron microscope. That is allows researchers to study samples in real time under real world conditions. For example, we can do in situ heating condition, in situ atmosphere, in situ gas condition, in situ liquid condition. So what is an atmosphere system? When we talk about the atmosphere system, we specifically mean the prototypes gas system. We are having it in our EPIC Center. This is what it looks like. It has a gas cylinders, the gas supply system, and also the holder. It can be used in the microscope. In EPIC, we put it in DAM 200 room. This is the specifications of the gas system here. Based on the microscope and the samples, the resolution can reach 0.5 angstrom. The pressure for the atmosphere system is from 1 torr to 760 torr, which is 1 atmosphere pressure. It cannot go to higher than 1 atmosphere pressure is because we are having a silicon nitride window. If the pressure is too high, it will break the window. So for safety concern, we keep the pressure is about 1 atmosphere. Comparing to the environmental microscope, this pressure is it's kind of a high pressure in a microscope. The temperature of the sample, we can have it from room temperature to 100 degrees Celsius at the maximum 10 degrees Celsius per second, which is very fast in heating rate. So this is a marketing video from the company. We can see this is general introduction of the in situ. This is how the chips assembles into the holder, and this like sealed by the lid and screws, and the electrode heating, and the control system and the holder, how it assembles to the microscope, and schematically showing how the gas flow from the gas control to holder until it reach your sample. As it shows, we do have the EDS and the EOS compatibility in our gas system here. So if you assemble the samples very well and the component of some of your sample is very good, it's possibly you can reach the atomic resolution in gas system. This is instruments we have in EPIC Center. We have very cutting-edge microscopes here. One is ARM 200, which is aberration corrected. The other is ARM 300, with we call it the grand arm. It's dedicated to in situ work. So we have 3 different types of holders or capabilities currently. We have liquid holder, we have heating holder, and we have the gas holder. So that means you can do this type of the in situ liquid, gas, and heating in our center. So this is the generally instruction of the atmosphere system. This just have this 4 part. First is a gas control system. This is used to mixer gas and control the pressure of the tip area of the holder, control the vacuum of the tip of the holder, and also the heating control is also in this part. The second is the atmosphere controller, or we can call it the software. It's very user-friendly software. It's very easy to operate and easy to understand. So this is a holder, how the holder looks like, and because this is a heating gas, so it should be the electrode chips. So we call it the E-chips. It has the heating electrode, and it has those membranes on the on the window area. This is how we assemble the holder. This is a zooming of the tip area, and this is how it looks like when it's assembled. So we can see that these two parts is a gas inlet and outlet. There's no preference which is inlet, which is outlet. You can select each one as in and the other is out for the gas flow. We have this D is a gasket. It's kind of the assembly of the two O-rings to seal the two chips, smaller and big chip, to prevent the gas leak to the microscope. And then use the lid and screws to tighten this part together to make sure we have a isolated gas environment from the vacuum column of the microscope. Based on the lid, on the lid, you can see there is a gap. So this gap can enable the EDS mapping and the use mapping. So one beauty of this one is that we have a back valve of the holder. Using this back valve, even if you do not close or loop the inlet and outlet of the gas, you can still seal the holder to do some post in situ observation or prevent the leak of the gas. So this is our schematic of how the heating membrane or how the E-chip looks like. For both of the two chips, there are some silicon nitride membranes on the silicon wafer. So for the spacer of this gas, the spacer of this gas chips is fixed at 5 micron thick. Because not like the liquid, the thickness of liquid will affect the resolution dramatically. But for gas, we know that it's very light. Even if we have 5 micron thick, the effect of the resolution is very minor. We have silicon nitride membrane, which is electron beam transparent. We saw this for this six circle. They are the silicon nitride on the brown area. This is a ceramic heating membrane. The heating membrane is a silicon carbide. You can see it under the microscope, like the at the right bottom image. But if your sample is sitting on the heating membrane, you can still you can still see a sample, but the resolution is very bad. So the ideal places to look at the sample is this 6 silicon nitride window area, which is each one is a 9 micrometer diameter is 9 micrometer. So you totally have 6. So that's enough for you to do some key observation. This is a gas delivery system. So the gas delivery system has 2 reaction tank and 1 vacuum tank. For each reaction tank is 1 liter. For the vacuum tank is 2 liter. So you can understand the mass here. 1 plus 1 is 2. So we can come here. This is a tank 1, tank 2 is a reaction tank, and the vacuum tank is at the bottom. So for each reaction tank, you can set up the different pressure and the different mix ratio of your gas. You can design your gas up to 3 different components at the random ratio you decided. For the gas line, it's not fixed. You can select what type of gas you want to connect it, but the one thing you need to keep in mind is the gas should be safe to the system. This area monitor the flow rate, the pressure, and also the temperature of the holder tip. And the data view area, you can live to look at your pressure and your flow rate and your temperature. And also you have
Kun, you're muted.
Can you hear now?
Yes.
Yeah, we can hear now.
So since when I was muted?
Just for a few seconds.
Okay, that's good. I don't know why suddenly.
No worries.
Yeah. So We have 2 reaction tank, and for each tank, you can set up different gas mixture at different ratio for 3 different, up to 3 different gases mixture. The pressure can also be different too. During the experiment, you can select which tank, tank 1 or tank 2 as your reaction tank. So that means you can do your sample for 2 different types of gas experiment at one set. All the parameters can be monitored and recorded as this data view area. You can select which function you want to monitor. You can see the holder's temperature, holder's pressure, holder's flow rate. Also, you can also see the vacuum tank pressure too. It really depends on you. So this is the right side here panels here is a gas control. So you can set up your pressure, your flow rate, and even during the experiment, you can do the adjustment for the flow rate. But as for the pressure, once it's set up, it's fixed. You can't change it. You need to set it before your experiment. You can also do the temperature control. The temperature can up to 1000 degrees Celsius, and the heating rate is up to 10 degrees Celsius per second. So it's really fast. The cooling rate is also the same, 10 degrees Celsius per second. This for the target system, you can do the pump part of the whole system, and for here you can do the pump part or clean each part of the whole gas control system. Like the gas holder, you can pump part the holder Olin, you can pump part the tank 1 or tank 2 Olin, or even for the gas input lines, S1, 2, 3, you can also clean them, because sometimes if you switch gas, like for the hydrogen, we switch from hydrogen to oxygen or to carbon dioxide, we always have some hydrogen residues in the tubings in the tubing. So we will close the valve on the cylinder and do the cleaning pump part of the supply line, input line, and so you will make sure you have the cleanest gas you have. We also have some vapor capability, like you can do the water vapor, you can do ethanol, methanol vapor. But the pressure cannot. If you do the vapors, the pressure cannot reach about 1 atmosphere, because we know that at 1 atmosphere, water cannot maintain the vapor status. It will become too liquid. So the pressure depends on the pressure, how like as a water, as an example, if you do the vapor kit of the water, the maximum pressure of the water will be 80.6 torr. If you, it will be the pure water. If you want to mix water with some other gas like the argon or nitrogen, it will be the ratio. You can calculate the final pressure based on the ratio of water and the balanced gas. So we also have RGA, which is a residual gas analysis at the outlet of the gas line. So it will analyze the component of the gas after the reaction. So the sensitivity is supposed to be very, very high. It has a turbo pump to make sure when the RGA is turned on, the system can go to a lower, can go to a better vacuum condition. So this is an example of this is the RGA example to show how clean the system will be after 10 cycles of the pump purge. After 10 cycles, you can see the pressure of the hydrogen, which is as the highest is reach about 10-8 level, or which is very low. So it always has the hydrogen residues, is because for in most of the gas, hydrogen is a light and it's very hard to be removed. So they always have some hydrogen residues. This is a sample from the company. It's a collaborated. It's courtesy to Professor Erson's group. This is the RGA example. What they have done using the nickel to do the methylation of the carbon dioxide. So the final product should be methane and water. They increase the temperature from 300 degrees Celsius to 900 degrees Celsius in 8 hours, and then finally plug out this flow chart to show how pressures changing for different components. Because you can see with the productive, the methane and the water here, the blue and the yellow increase. For the reaction gas, the green and red are decreased. So this is a general introduction of the gas system. But when we're talking about the application of the atmosphere system or gas system, we always use it in catalysis, corrosion, oil, gas, and semiconductors. This is some applications we have done here in EPIC Center. This is the oxidation of the copper nanowire in carbon dioxide at 200 degrees Celsius. For this one, it's clearly we can see how the oxidation started and how it developed. By analysis, we can conclude that this is a carbon diffusion of the copper ion and not the oxygen. But without this in situ observation, you can't get any conclusion like this. For this one, is a vapor. It's a corrosion of silver copper in water vapor. There's at room temperature. This one is at room temperature. So once we flow the vapor in, we find that the corrosion always starting at the copper side. It will protect the silver first. Once the copper are totally gone, it is the corrosion of the silver will start. So this one is the one we want to do the demo of the RGA, but we didn't get it, before this kind of the pandemic period because something wrong with the RGA. We send it back for fixing, and currently we get it back and fixed. We will do the testing of the RGA in the following months. We're trying to demo the similar chart as that Professor get. So this one is a gold reduction in silica shell. Because this synthesis of the silica shell is has a lot of organic things, so it's really need to pre-treat the samples before we put it into the holder. So this one is very interesting, is because we do use this gas system to observe the copper reduction in MOF structure. For the last one is we use a normal detector at a relatively high dose rate, and we can see the collapse or shrinkage of the MOF structure. But in the meantime, we can still see some bright spots at the dark field or dark spots at the bright field, which is copper nucleated inside the MOF structure. For the right video, we are using the K2 camera at a low dose condition. So we can see we can see how the copper reduced in the MOF structure, and you can notice that once we zoom in, we higher the dose rate, the MOF will be degraded. So this is generally how we use this one. Another application of the gas system is you can use FIB to FIB section your sample and align, because our gas holder is single tilt. You need to just precautionally get your zoom axis of your sample and use the FIB to mount it on the chip. Just to make sure you can adjust the X tilt so you can get correct zoom axis of a sample. And then you can get a very good, beautiful atomic resolution image. But for that one, you really need to be an expert of the FIB. So thank you. If you have any questions, I will look at the chart. Okay. Let's see. What gas and liquids are currently allowed for this system? So first answer question from Yep Wang Chuang. So for the gas system, currently what the gas we have is about carbon dioxide, hydrogen, oxygen, carbon monoxide mixed with oxygen, and also we have argon. We are ordering some ammonia gas currently. So if your gas is not very corrosion, it will be safe to our system. For the liquid, I'm not pretty sure you are asking about the liquid cell or the vapors for gas system. If it's vapors for gas system, it need to be like some like some liquid that you can vaporize it at some pressure is like water. Like water, as long is very easy to be vaporized. Some if it's very dense, it's very hard to be vaporized. The liquid will not work. The second one, Matthew, what's the temperature range limitation for the in situ heating for your instrument? So we have two different types of heating. One is the in situ gas, the other is the in situ heat. For the in situ gas, the temperature range from room temperature to 1000 degrees Celsius. For the in situ heating, it's a separate holder. The temperature range is a little bit higher. It's from room temperature to 1200 degrees Celsius. Yeah, Xiaoping already answered the first question. Matthew, okay, Eric, do different between the effect of gas vapor on the sample? Gas or water vapor on samples compared to the damage of the. Okay, normally, if we want to differentiate the effect of the gas or water or vapor, and also comparing to the beam damage. So the first thing is that you can run an experiment that's with the beam on and with the beam off. So we put the holder in and we put the sample. We find the one sample and we totally turn off the beam. We run the experiment to see how it looks like. That is the best way to illuminate the beam image, the beam effect on your sample. But based on my experience, for most of the tests, the beam always has some effect on your sample. So like even for we have 6 different view areas. So we always can focus on one window and we do the observation on there, and we find that the mechanism might be the same. So like if we do the experiment for long enough, the phenomenon will be the same for the electron beam irradiated area or non-irradiated area, but the dynamic things are always a little bit different because the electron beam always accelerates the process. Yeah. So I think that's all the questions currently. So if you have more, you're welcome to ask.
Thank you, Kun.
No, it's okay. Any effect of temperature on the electron beam? Do users need correction or calibration? Yes, definitely. Do users need correction or calibration once heat is turned on? Yes, there's one tricky part of the in situ gas is that because the windows are silicon nitride, we always have a pressure change during experiments. Like when you flow the gas in, the pressure is atmosphere. When you do the pump part, the pressure is you can decide which pressure you want it down to. Normally we down to the 1 torr. If the pressure is 1 torr, the two windows the two silicon nitride will near to each other. If it makes the pressure back to the normal, it will bulge to the distance between two silicon nitride window will be larger. So the sample on the window is always jumping up and down all the time. So the Z distance is always changing. So you need to make sure you do the imaging and everything at the atmosphere, and then at atmosphere before you flow the reaction gas, and then and then when you flow the reaction gas, you will have most similar condition. And another drift heating effect is that we always have heating drift for the during the in situ gas experiment. So sometimes it depends on how fast you hit your sample. If you hit sample about 10 degrees Celsius per second, most of cases you will lose your sample because it will dramatically drift out of your view area. Sometimes so you need to keep eye on, and then you need to find it, readjust the Z of your microscope and find your sample again if you hit your sample very fast. if you hit sample relatively slow, you can continuously adjust the Z and the focus of your sample and then keep tracking on your particle. But the good thing is that we are going to have an Axon system, which is a drifting correction software. So it will make life easier once we get that system. More questions? We do not have the Axon drifting correction software currently. We will have it soon. That's for Matthew's question. Do you have the Axon drift correction software? Yes, I did one test. Is one is one is the fill the gas with with 5 micron spacer, and the other is we vacuum the gas to 1 torr. We can see the difference of the resolution difference of the sample. So if we can reduce the spacer to 200 nanometer, it do helps about the the resolution. But one thing, another concern is that first we want to make sure the sample contacts as much gas as possible. Maybe the 5 micron helps a lot. We can make sure there are enough gas for the particle contact with the gas. The other is that the resolution increasing by reducing the spacer is not so obvious or so dramatically. So it will work, but it not works as much as we thought. More questions? Yeah, another thing is that we are welcome all the users from the Northwestern University or from UIC or the Chicago area to contact us or consult your experiment or your scientific problem with us to discuss is that possible to carry out your problem with our gas system. You know that everything is very slow during this COVID-19 period, but we will do it finally. But we will set up some meetings to discuss the possibility and how will we carry out the experiment. So if you have some interesting idea, you are really welcome to contact us. Is there any more questions?
Okay, I think we're good.
Okay.
If anyone has more questions, thank you for attending.
Thank you, Quinn.
Yeah, you're welcome.